Every plan to colonize Mars is built on a number nobody has tested. Not the fuel calculations, not the habitat specifications, not the radiation shielding ratios or the hydroponic yield projections or the launch window timing constraints. Those have been tested, modelled, revised and refined across decades of mission architecture work by serious engineers at serious institutions. The plans are detailed, the renders are beautiful, the spreadsheets are long. The number nobody has tested is 38. 38%. Mars gravity as a fraction of Earth's, not 0, which we understand with extraordinary precision, not 100, which we were born into, and which shaped every organ and tissue in the human body across 4 billion years of evolutionary history. The middle ground, the number that looks almost right, the number that has been used as a design parameter in every Mars colonization plan ever written, as though it were a known quantity, when it is in fact the largest single unknown in the entire enterprise. In March 1995, a Soviet cosmonaut named Valery Polyakov was lifted from a Soyuz capsule in Kazakhstan after 437 days aboard the Mir space station, the longest any human being has ever remained in space, before or since. His legs had forgotten what gravity was. His skeleton had shed 1 to 2% of its density every month for 14 months. His cardiovascular system had reorganized itself around weightlessness. He had to be carried from the capsule. He could not walk. He recovered, slowly, over months, at full Earth gravity. On Mars, the gravity is 38% of Earth's, not 0, 38%. And here is the specific problem. We have no data on what 38% gravity does to a human body over years. We have extensive, high-quality, well-replicated data on what 0 gravity does, because Polyakov and hundreds of other astronauts gave us that data. We have the entirety of human evolutionary history telling us what full Earth gravity does. But the number in the middle, the 38% that every colony plan assumes is close enough, has never been studied at the timescales a colony implies. Never. Not once. Not in any environment that approximates it. Polyakov came home to Earth, and Earth caught him. The colonists on Mars will have no Earth to come home to. If this kind of careful, unhurried thinking about the real frontier of what we are attempting is something you want more of, subscribing to this channel costs nothing, and it helps. Now let us begin. Every diagram you have ever seen of Mars colonization is lying to you. Not about the distance, not about the dust storms or the perchlorate-laced regolith, or the bone-dry surface or the radiation that scours everything that stands above it. Those hazards are acknowledged in every serious treatment of the subject, catalogued in technical documents, modelled in risk assessments, and addressed, or at least nominally addressed, in the engineering architecture of every major Mars mission proposal currently in circulation. The lie in the diagrams is subtler, it is structural, it lives in the way every architecture document, every public presentation, every funding proposal treats the 38% gravity number as a solved design parameter, rather than the most critical open question in the entire enterprise. There are 2 gravitational regimes for which we have real biological data. We know, with extraordinary mechanistic precision and a rich epidemiological record, what full Earth gravity does to a human body. We have been running that experiment continuously for the entirety of human evolutionary history. Every organ, every tissue, every physiological system in the human body was shaped by a full 1G gravitational field across 4 billion years of biological refinement. We know the result intimately because we live in it. We know, with nearly as much precision, what 0 gravity does to a human body across the timescales of the longest missions flown. Valery Polyakov gave us 437 consecutive days of data from a single individual. The International Space Station has been continuously occupied since November 2000, and in that time, hundreds of astronauts from dozens of nations have contributed to the most detailed dataset on human response to weightlessness ever assembled, covering mission durations from 2 weeks to 1 year. The patterns in that data are consistent, well characterized and well published. Astronauts return from 6-month missions with bone density losses of 6 to 12% in the weight-bearing skeleton. They return with cardiovascular deconditioning, with fluid shifts toward the upper body that alter intracranial pressure and in some fraction of cases cause permanent damage to vision. With immune system changes, with muscle atrophy severe enough that returning crew members sometimes need assistance walking from the capsule to the medical tent. We know all of this. The database is rich, and the conclusions are firm. The most dangerous number in spaceflight is the one that looks almost right. What we do not have is a single data point on what 38% gravity does to a human body over the timescales that a colony implies. Not 6 months, not a year, not the length of the longest mission anyone has flown, over the length of a life, over a decade, 2 decades, a generation. There is no rotating habitat aboard the ISS providing a continuous 0.38 G environment for medical study. There is no free-flying space laboratory running a long-duration partial gravity experiment. There is no analog facility on Earth capable of producing 38% gravity and maintaining it for years while study participants live and work inside it. The bed rest studies that researchers use to simulate some effects of reduced gravitational loading, tilting participants at a head-down angle for weeks at a time, provide hints about partial unloading. Those hints suggest that the rate of physiological change decreases as gravitational load increases. Partial loading is better than zero loading. But hints derived from a few months of bed rest studies conducted at Earth's gravity are not the same as data collected from human beings living in 38% gravity for years, and data is what a colonist's skeletal future, cardiovascular future, and visual future depend on. Consider the bone loss math applied honestly to a colony timeline rather than a mission timeline. Bone loss in zero gravity runs at approximately 1 to 2% per month in the weight-bearing skeleton, concentrated in the femur, tibia, and lumbar vertebrae. The bed rest data suggests that partial unloading reduces this rate. Suppose, on the generous end of what the partial evidence suggests, that 38% gravity cuts the bone loss rate in half compared to zero gravity, 0.5% per month instead of 1%. In year 1 of surface living, the colonist has lost roughly 6% of bone density in their legs. Significant, measurable, but within the range of what ISS astronauts experience and recover from with rehabilitation. Now extend the timeline, because a colony is not a mission. A colony is a permanent settlement. The people in it are not going home. 12 months times 10 years times 0.5% per month is 60% bone density loss in the weight-bearing skeleton over a decade of surface living. A person who has lost 60% of femoral bone density is not a productive member of a labour-dependent colony. They are at extreme and continuous risk of fracture from ordinary activity, walking on uneven ground, carrying a moderate load, stepping down from a platform. Any of these can fracture a bone that has lost 60% of its structural material. On Mars, without an orthopedic surgeon, a fractured femur is not an inconvenience. It is a potential death sentence. At minimum, it converts a productive colonist into someone who requires extensive care from people who are needed elsewhere. We have covered a lot of ground. Take a breath. The psychological dimension of the 38% gravity problem compounds the scientific one in a way that mission planners rarely discuss publicly. The decision to proceed with a Mars colony before resolving this question is not being made by people who are unaware of the gap. The space medicine researchers know the data exists for zero gravity and does not exist for partial gravity. The engineers designing habitats know the structures are being built for a population whose long-term health response to the gravity environment is an open question. The mission architects know that the biological foundation of their plans has not been tested at the relevant timescale. They proceed anyway, for reasons that are not entirely unreasonable. The argument is that waiting for perfect information before proceeding means never proceeding, because new unknowns emerge with every new discovery, and at some point the risk of never going exceeds the risk of going without complete knowledge. This is a legitimate argument in the abstract. It is also an argument that places the cost of the knowledge gap onto the colonists themselves, rather than onto the planning process. The colonists will generate the data. Their bodies will close the gap in the database. The mission will know, within a decade of the first long-duration settlers arriving, what 38% gravity does to a human being across a lifetime. But the settlers will already be there, already adapted to whatever the answer turns out to be, already living inside the results of an experiment they agreed to participate in, but could not fully understand when they agreed. The first settlers will not know, when they press their boots into the rust-coloured regolith for the first time, how their skeletons will look in 10 years. They will not know whether their hearts, adapting year by year to the reduced gravitational demand of 38% G, will have the reserve capacity to handle the physiological stress of a serious infection in year 8. They will not know whether children born on Mars will grow with the same bone architecture, the same vestibular system calibration, the same cardiovascular geometry as children who grew in a full gravitational field. Those children will be the data point. Their lives will close the gap. And unlike Polyakov, who was extracted from the experiment when the mission ended, there will be nowhere to send the results when they come in. The compounding barrier stack that emerges from taking all of these challenges together, rather than examining each in isolation, is more formidable than the sum of its parts. A colonist who is managing their radiation exposure within accepted limits, while also managing bone density loss, while also managing the psychological weight of isolation, while also doing the physical labour of maintaining a habitat, while also managing a nutritionally constrained diet, is not facing 4 independent challenges. They are facing 4 challenges that interact with each other and compound through each other. Nutritional restriction affects immune function. Weakened immune function increases susceptibility to infections. Infections that become serious in a resource-limited medical environment create the cascade failure conditions described earlier. The radiation that damages DNA is more dangerous in a person whose immune surveillance is compromised by the stress of sustained isolation and nutritional constraint. The psychological burden of operating under sustained physical risk in an environment where every system failure is potentially fatal is not independent of the physical burden of the physical risk itself. They reinforce each other. They compound. The mission does not fail because something dramatic happens. It fails because nothing dramatic happens for so long that the quiet accumulation of 1,000 small degradations exceeds the crew's capacity to cope. That sentence, written in Script 4's DNA as the most important insight about interstellar travel, applies with equal force to a Mars colony. The failure mode is not the spectacular explosion or the sudden catastrophic decompression. Those can be anticipated, planned for, and if they occur, acknowledged as the disaster they are. The failure mode is the slow, silent, invisible accumulation of bone loss and radiation exposure, and nutritional deficit and psychological erosion and equipment degradation and pharmaceutical depletion and institutional memory loss, none of which individually crosses a threshold that triggers an emergency response, until the day when the combined weight of all of it simultaneously is more than the community can carry. The historical specificity framing helps make the timeline concrete. A decade of surface living in 38% gravity is not an abstraction. 10 years ago from today was 2014. In 2014, smartphones were already ubiquitous. Social media had already reshaped public discourse. The Mars colonist who lands on the surface in whatever year the first crew arrives and remains there for a decade is experiencing a span of time equal to a decade of normal Earth life, with all the accumulated change and development that a decade implies, except that every day of it occurs in a gravity field whose biological consequences across that full span are unknown. The changes in their body across that decade, the bone density they have lost, the cardiovascular adaptation that has occurred, the cumulative radiation dose that has accumulated, the psychological adjustment to permanent isolation from Earth, will not be reversible by returning to Earth if returning becomes possible or necessary. The body that lands on Mars at 35 and the body that has lived in 38% gravity for 10 years are not the same body, and no intervention available on Mars or on Earth will return the second body to the state of the first. The analogy to the speed of discovery matters here. When researchers first began measuring bone loss in zero-gravity astronauts in the 1960s and 1970s, the magnitude of the problem was not immediately apparent because early missions were short. It took decades of progressively longer missions and increasingly sophisticated measurement techniques to establish the 1 to 2% per month rate with confidence. The partial gravity question has not had that time because no mission architecture has ever placed a human being in partial gravity for longer than a few days at a time, typically during lunar surface operations on Apollo missions, where crew members spent at most a few days on the surface. A few days is not enough to detect a rate of physiological change that unfolds over months and years. The gap in the database is not a gap that someone forgot to fill. It is a gap that the current history of spaceflight has not yet produced the conditions to fill. And the Mars colonization plans are being designed as though that gap does not exist. The deeper implication is that the 38% number functions as a cognitive anchor in exactly the way that Script 4's evolution trap technique describes. Your brain has been shaped by millions of years of evolution on a planet where the difference between 38% of something and 100% of something is a distinction that almost always matters in an immediately practical way. You walk into a room that is 38% lit, and you can navigate it, imperfectly, bumping into things, missing details, but navigating. You receive 38% of your normal caloric intake, and you are hungry but functional, your body drawing on reserves. These analogies feel relevant because your threat detection system evolved to make them relevant. In most survival-relevant contexts, 38% of adequate is meaningfully better than zero, and meaningfully better than zero is a significant and actionable difference. In the specific context of gravity and human physiology over years, the analogy breaks down completely, and the breakdown is not visible to intuition. You cannot feel the difference between 38% gravity and 100% gravity the way you can feel the difference between 38% light and full light. You feel lighter in 38% gravity, which the body interprets as pleasant. You feel more capable of physical effort in certain ways, which the body interprets as an advantage. The signals that would warn you that your bone remodeling system has shifted out of balance, that your heart is slowly adapting downward, that your fluid distribution has begun to change in ways that will affect your vision, are not signals that the human sensory system was ever equipped to receive. Evolution did not build a gravity deficit alarm into the human body, because for the entirety of human evolutionary history, no human being ever spent more than a fraction of a second in reduced gravity. The fall was brief. The landing, if survived, returned full gravitational load. The body never needed a warning system for sustained partial gravity, because sustained partial gravity was never a condition any of our ancestors encountered. The colonists on Mars will be the first human beings who ever need that warning system, and they will not have one. The degradation will be silent and invisible until it is already far enough advanced to be consequential. Every year that passes without answering this question is a year spent building a more detailed and expensive plan on top of a foundation that nobody has verified. In zero gravity, bone is not a passive structural material sitting inertly in the body. It is a living tissue, continuously remodeled throughout your life by a paired system of cells whose activity is exquisitely sensitive to mechanical signals. Osteoclasts, one type of cell, continuously dissolve existing bone mineral, releasing the calcium and phosphate it contains back into the bloodstream. Osteoblasts, the complementary type, deposit new bone mineral in the spaces the osteoclasts have cleared. On Earth, the mechanical stress of bearing your weight against gravity with every step you take Every time you stand, every time you carry a load, transmits through the skeleton and is detected by a third type of cell called osteocytes, which are embedded in the bone matrix and function as the mechanosensory system that regulates the whole process. When the mechanical stress signal is adequate, the remodeling process runs in approximate balance, and total bone mass remains roughly stable. When the signal falls below the threshold the body interprets as adequate, the balance shifts. The osteoclasts keep dissolving old bone at their normal rate. The osteoblasts slow their deposition of new bone. The net result is progressive bone loss at the rate of approximately 1 to 2% per month in the weight-bearing regions of the skeleton. This is what happened to Polyakov across 437 days. His bones were doing exactly what bones rationally do when the signal that normally maintains them disappears. His body was not failing. It was adapting perfectly, efficiently, rationally to the environment it was actually in. A zero-gravity environment does not require a weight-bearing skeleton, and the body reduced the maintenance energy it was spending on one. He recovered. It required months of supervised physical rehabilitation on Earth, and it required the full gravitational environment of Earth to make that rehabilitation effective. The mechanical loading stimulus of walking and exercising at 1G was not incidental to his recovery. It was the mechanism of his recovery. Earth's gravity was the medicine, and without it the rehabilitation could not have achieved what it achieved. Polyakov is, by most accounts, in good health. He is fine because he came home to the planet that had made him, and that held the tools his biology needed to rebuild what the experiment had changed. Now consider what happens in 38% gravity, not zero. Not enough to be confident the process works. The bone remodeling system will receive some mechanical signal from the partial gravitational load. Partial loading is better than zero loading, as the mechanobiology would predict. The rate of net bone loss will be slower than in zero gravity. The question is, how much slower? Slow enough to be compatible with skeletal health across a decade of surface living. Slow enough that the colonist at 45 is not dangerously fragile? Nobody knows. The relevant data does not exist. What comes next will make sense once this has had time to land. Muscle loss runs in parallel with bone loss, and compounds the picture in ways that interact with each other rather than running independently. The postural muscles of the lower body, those that work continuously against gravity during every moment of standing, walking and moving in an upright posture, receive reduced demand in any lower gravity environment and adapt accordingly. They reduce, not immediately and not dramatically but steadily over months and years, toward the workload they are actually being asked to perform. The process is not malfunction. It is the rational efficiency of a biological system that does not maintain capacity it is not using. The heart is a muscle. It adapts continuously to the demands placed on it, enlarging when those demands are chronically high and reducing when they fall. On Earth, the heart works against the full force of gravity with every beat to push blood upward from the lower extremities through the venous system back to the right side of the heart. This is a significant and continuous gravitational load, and the heart is sized in part to meet it. In 38% gravity, that gravitational work is substantially reduced. Over years of Martian surface living, the heart adjusts downward, quietly, without the colonist noticing, without pain or obvious symptoms, toward the workload it is actually being asked to perform. The adaptation is rational and efficient, as all biological adaptations are. And a heart that has adapted to years of reduced gravitational demand may not have the reserve capacity to meet the sudden, extreme requirements of a medical emergency, or the sustained physiological stress of a serious systemic infection, or the demands of intense physical labour during a critical habitat repair. The fluid redistribution effects observed in long-duration ISS astronauts add a dimension that was not even recognised as a problem in space medicine until relatively recently. Without gravity pulling body fluids consistently downward, the distribution of fluid throughout the body shifts. More fluid accumulates in the upper body and head. The increased fluid volume in the cranial compartment changes the pressure of the cerebrospinal fluid that surrounds the brain and spinal cord. Elevated intracranial pressure pushes on the optic nerve at the point where it exits the back of the eye, changes the geometry of the posterior segment of the eyeball, and in some fraction of astronauts causes changes to visual acuity that persist long after the mission ends. The condition, known as spaceflight-associated neuroocular syndrome, has been documented in a significant fraction of long-duration ISS crew members, some with structural changes to the optic nerve that appear permanent. Whether 38% gravity prevents this fluid redistribution entirely, or only slows it, or allows it to develop on a longer but still significant timeline, is not known. The anatomy of the human eye did not evolve with Mars in mind. What we have, taken together, is a picture of a body being slowly and quietly renegotiated by its environment. Not dramatically, not with pain or obvious warning in the early years. Below the threshold of daily awareness, month after month, the skeleton thinning, the heart adapting downward, the postural muscles reducing, the eyes changing. All of it accumulating in the background while the colonist is focused on the work of survival, the 100 tasks that keeping a human community alive on another planet requires. The person who lands on Mars at 35, healthy and strong and among the most rigorously screened individuals ever sent off-world, may feel capable and productive through their first year, their second year, perhaps their third. The person still there at 45, having lived a decade in a gravity field that evolution never anticipated and that medicine cannot yet fully characterize, is living inside a substantially different body. A body that the planet has been quietly remaking without anyone's explicit consent, in directions that the mission architecture did not fully account for, toward an endpoint that nobody has yet observed in any living human being. The dust adds another dimension that is easy to underestimate. Martian dust is not like terrestrial dust. Earth dust particles, produced by geological and biological weathering processes, tend to be relatively rounded and chemically inert. Martian dust particles are fine, angular, and chemically reactive. The perchlorate content of Martian regolith means the dust that will inevitably find its way through suit seals into airlock cycles and into the habitat atmosphere carries a chemical payload that is not benign to human tissue. The history of occupational lung disease on Earth, from coal miners' pneumoconiosis to the silicosis of quarry workers, to the asbestos-related diseases that killed thousands of insulation workers over decades, all followed the same pattern: extended periods of apparently manageable exposure, followed by the emergence of irreversible lung damage that became visible only after it was already too late to reverse. The colonists will breathe filtered air inside the habitat, and the filtration systems will be maintained as well as the colony's resources allow. But no filtration system is perfect, and chronic low-level inhalation of reactive Martian dust particles across years of surface operations is a health variable that will be managed imperfectly at best. The isolation problem, distinct from but interacting with every other challenge discussed in this script, adds a dimension that physical challenges alone cannot capture. The ISS crew, however distant they are at 250 miles above Earth's surface, can speak with family and friends with a delay measured in fractions of a second. Earth is always visible through the porthole as a luminous blue-white sphere, impossibly beautiful, impossibly present. The Mars colonists cannot speak with anyone on Earth without a communication gap measured in minutes to tens of minutes each way. Earth, when visible in the Martian sky, is a bright point no larger than Mars appears to the naked eye from Earth. The psychological weight of that specific distance, of the communication gap that makes spontaneous conversation impossible, of the knowledge that the familiar world is not a few hundred miles overhead but tens of millions of miles away and getting farther, will be a sustained presence in every colonist's mental life throughout their time on the surface. Long-duration isolation studies, including the Mars 500 simulation in which 6 crew members spent 520 days in a confined facility in Moscow, documented depression, sleep disruption, interpersonal conflict, motivational decline, and cognitive performance degradation under conditions far less extreme than actual Martian isolation. The psychological infrastructure required to sustain healthy functioning across years of this specific isolation has no tested framework. Sit with that for a moment. The bone loss does not announce itself with pain until it is already too late to reverse. That is the nature of the trap. If this kind of careful, unhurried thinking about the real frontier of what we're attempting in space is something you want more of, subscribing to this channel costs nothing. It helps this work reach people who are thinking seriously about where we're actually going. There is more to cover tonight. The radiation problem is commonly presented as solved in principle and awaiting implementation. The logic runs: we understand the dose rates, we build thick walls, we pile regolith on top of the habitat, we limit surface EVA time, we track lifetime dosimetry, the way nuclear industry employers track occupational exposure on Earth. Informed adults accept elevated cancer risk as a known occupational hazard, the way test pilots accept elevated mortality risk, the way deep-sea commercial divers accept elevated risk of decompression injury. The problem is understood. The solution is engineering and informed consent. Move on. That logic is missing the numbers that tell you what accepting it actually means in biological terms. The average person living on Earth receives approximately 2 millisieverts of radiation per year from all sources combined. Background radiation from naturally occurring radioactive elements in soil, rock, and building materials. Cosmic rays filtered by the atmosphere and deflected by the magnetosphere. Medical diagnostic imaging. Trace radioactive isotopes present in the food supply. 2 millisieverts per year is what normal looks like. It is the baseline against which radiation protection science measures everything else. A professional radiation worker in the United States, a person whose job involves regular contact with radioactive materials and who is subject to regulatory oversight specifically because of those working conditions, is permitted a maximum occupational dose of 50 millisieverts per year. This limit is not arbitrary. It reflects decades of epidemiological research from nuclear plant workers, from radiation oncology technicians who worked before modern dosimetry existed, and from the long-term follow-up of atomic bomb survivors, collectively establishing the quantitative dose-response relationship between cumulative radiation exposure and elevated cancer risk with sufficient statistical precision to set a regulatory line. On the surface of Mars, without a habitat overhead, the annual radiation dose is approximately 300 millisieverts. This number is not derived from theoretical models alone. The Mars Science Laboratory mission's Curiosity rover has been measuring the actual radiation environment on the Martian surface with its Radiation Assessment Detector since landing in Gale Crater in August 2012, continuously for over a decade. The measurements are consistent, well-calibrated, and represent the best direct observational data available on the Mars surface radiation environment. 300 millisieverts per year, 150 times the Earth baseline, 6 times the annual limit for professional radiation workers on Earth. A dose level that's sustained continuously over a decade of surface living produces a cumulative exposure of 3,000 millisieverts. The habitat keeps the cold out. It does not keep the invisible in. Shielding reduces the indoor dose substantially, and this is an honest and important part of the engineering picture. 2 meters of Martian regolith covering a habitat can attenuate the indoor dose rate to somewhere in the range of 30 to 80 millisieverts per year, depending on shielding depth, construction quality, and the specific location. 30 millisieverts is still 15 times the Earth baseline that defines normal lifetime radiation exposure. 80 millisieverts is still 40 times that baseline and still at or above the annual occupational limit for radiation workers. But compared to the unshielded surface dose of 300, these numbers are meaningfully better, and if colonists remained inside the most heavily shielded portions of the habitat continuously, the chronic exposure would represent a high but potentially acceptable risk level for adults who had chosen this work with complete information about what they were accepting. The problem is that colonists will not remain inside the shielded habitat continuously. They cannot. The operations of a functioning colony require constant surface activity. Solar array maintenance requires regular physical inspection and hands-on repair. Greenhouse modules, even if structurally attached to the main habitat, require tending that exposes crew to less shielded environments. Construction of new infrastructure requires extensive surface time. Equipment that fails on the surface must be repaired by crew members physically present at the failure location. Every EVA, every moment spent outside the most heavily shielded portions of the structure, adds to the cumulative radiation dose at the full unshielded surface rate or some intermediate rate depending on location and shielding overhead. Let that settle before we go further. The atomic bomb survivor cohort from Hiroshima and Nagasaki provides the most direct and extensively studied data on the biological consequences of elevated radiation exposure in human beings. Their individual exposure records were reconstructed from the physical evidence of the detonations, combined with survivor location data, to estimate doses received by hundreds of thousands of people with unusual precision. Health outcomes have been tracked in this population continuously since 1950 by the Radiation Effects Research Foundation. The follow-up now extends to more than 8 decades. The dose-response relationship for radiation-induced cancer is, in this population, clear and statistically unambiguous. Even at exposures in the outer zones, in the range of 200 to 500 millisieverts from acute exposure in the minutes of detonation, elevated cancer rates are detectable and have been replicated across multiple independent analyses. The relationship is approximately linear at these exposure levels. Every additional millisievert adds proportionally to lifetime cancer risk. There is no known threshold below which ionizing radiation causes zero biological harm. A Mars colonist is not receiving the same kind of exposure as an atomic bomb survivor. The physics of chronic, continuous low-dose rate exposure over years differs from the physics of acute, extremely high-dose rate exposure over seconds. Some experimental evidence suggests that the body's DNA repair mechanisms may be somewhat more effective when damage is delivered slowly rather than acutely, and that chronic exposure may be slightly less damaging per unit dose than acute exposure at equivalent total levels. This is a legitimate scientific distinction, and it is incorporated into current radiation protection models. But it does not erase the cumulative dose math. Over a decade of Martian surface living, the total dose accumulates to levels that the linear no-threshold model, the conservative but scientifically defensible standard used by every radiation protection authority in the world, predicts will meaningfully and measurably elevate cancer risk in a substantial fraction of the exposed population. 38% of Earth's gravity, 0% of Earth's magnetic shielding. The magnetosphere that protects Earth's surface from the majority of the charged particle radiation filling interplanetary space is generated by the churning of liquid iron in the outer core of the planet. It extends tens of thousands of miles into space in all directions, deflecting the continuous stream of charged particles from the Sun and the galactic cosmic ray background that originates from sources far outside the solar system. This protection is not perfect. Energetic particles find their way through at high latitudes, producing auroras. Major solar events cause temporary increases in particle flux at Earth's surface, but for the vast majority of the charged particle radiation in interplanetary space, across the vast majority of time, the magnetosphere provides continuous and effective protection. The surface radiation environment on Earth is, in cosmic terms, extraordinarily benign. Mars lost its global magnetic field between 4.1 and 3.9 billion years ago, when its smaller iron core cooled faster than Earth's and ceased its convective churning. The consequences of that loss are written across the planet's history. Without the magnetosphere deflecting the solar wind, the atmosphere was gradually eroded over hundreds of millions of years, dropping from whatever pressure it once held to less than 1% of Earth's sea level value. The liquid water that had once flowed in the river channels and filled the lake basins evaporated and was photodissociated in the upper atmosphere, its hydrogen component escaping to space. The surface was exposed to the full radiation environment of interplanetary space, unfiltered and undeflected for 4 billion years. The colonists arriving on Mars will be living on that record. The galactic cosmic ray component adds a dimension that standard shielding analysis cannot address, because galactic cosmic rays are continuous and largely unshieldable. They originate from sources outside the solar system, primarily supernova remnants and active galactic nuclei, and they arrive at the Martian surface from all directions, day and night, regardless of solar activity. The most energetic galactic cosmic rays carry enough energy to penetrate hundreds of meters of water-equivalent shielding and emerge still capable of causing biological damage. Unlike the lower energy charge particles from the Sun, which can be meaningfully attenuated by practical shielding mass, the highest energy galactic cosmic rays cannot be stopped by any shielding thickness that a habitat can be constructed from. Over a decade of surface living, the accumulated galactic cosmic ray dose contributes meaningfully to the total radiation budget in a way that thicker walls cannot engineer away. There is a lot to absorb there. The clock starts running the moment the colonists arrive. It does not stop until they leave or die. The body does not forget a single millisievert. Suppose you are 4 months into your first year on Mars. The habitat is stable, the systems are functioning within parameters, and the daily routine has settled into something that almost resembles normalcy. You know the sound the CO2 scrubber makes during its cycling sequence at night, a soft rhythmic hiss that woke you the first week and that you no longer consciously hear. You know the quality of the light through the habitat porthole at different times of sol, the thin, pale character of mid-morning and the slightly warmer tones of afternoon, and the genuinely striking pink graduation of the sky before sunset that no photograph transmitted to Earth has ever fully reproduced. You have a log of the sunsets. The sky on Mars is beautiful in a way that is difficult to explain to people who have only seen photographs. You have an EVA scheduled this morning, inspection of the Southern Solar Array Bank, which has been showing a 17% efficiency drop over the past 3 weeks that remote diagnostics have not resolved. A physical inspection is required. You suit up in the airlock, running through the pressure integrity check with the automatic precision of someone who has performed it enough times that it has become reflex. You cycle through the outer hatch, you step onto the surface, the regolith compresses fractionally under each boot. The sky is its usual pale brownish pink. The sun is there, smaller and less imposing than it looks from Earth, doing its best from 141 million miles. At some point in the next 4 hours, a region of the sun's surface that has been building magnetic stress for 2 weeks releases it. A solar particle event launches a front of high-energy protons and heavier ions outward across the inner solar system at a substantial fraction of the speed of light. A monitoring satellite positioned between the Sun and Mars detects the event and transmits an alert toward Mars at the speed of light. The alert is the fastest thing available. The fastest particles in the event front are already in transit, travelling somewhat slower but not by much. The time between the arrival of the alert and the arrival of the most energetic particles is somewhere between 8 and 30 minutes, a range that reflects the uncertainty in event geometry, the energy spectrum of the particles, and the response time of the detection and communication chain. You cannot run from a solar storm on a planet with no shelter deep enough. On Earth, a solar particle event does not constitute a surface hazard. The magnetosphere captures the incoming charged particle flux and routes it toward the polar regions, where it excites the upper atmosphere and produces auroras. The atmosphere absorbs what the magnetosphere allows through. A person standing on the ground during even a major solar particle event receives a dose so negligible that it is lost in the noise of their background radiation exposure. On Mars, neither of those protective layers exists. The atmosphere at less than 1% of Earth's sea level pressure provides modest attenuation that varies with location and terrain but cannot substitute for the magnetosphere. In a major solar particle event, the dose rate at the unshielded Martian surface can spike to levels that, sustained for several hours, deliver cumulative doses approaching or exceeding the threshold for the onset of acute radiation syndrome, the clinical condition that results from high doses delivered over a short period. The protection is mass interposed between the colonist and the incoming particle front. The habitat with its regolith shielding provides that mass and offers meaningful protection during major events. A spacesuit provides almost none. A spacesuit is designed to maintain pressure, temperature, and oxygen supply. Its radiation protection is approximately equivalent to a thin layer of water. It was not designed to be a radiation shelter, and it cannot function as one. The colonist on the surface during a major event needs to be back inside the shielded habitat immediately. How quickly that's possible depends on the distance to the habitat airlock and what they were doing when the alert arrived. If the solar array is adjacent to the habitat structure, the margin is comfortable. If the array is a kilometre away, which it might be in a colony that has grown beyond a single habitat module, and if the colonist is in the middle of a repair that cannot be safely abandoned in the first 60 seconds, the calculation changes. If the warning margin sits at the short end of its range, or if the monitoring system has a coverage gap at the time of the event, or if the event is unusually fast and the particle front outpaces the alert, the colonist may receive a significant acute dose before reaching shelter. Major solar particle events are not daily occurrences. They cluster around the peak of the 11-year solar cycle and are sporadic even then. There is no forecast that reliably predicts specific events days in advance. The only reliable warning is the detection of an event already in progress, with particles already in transit. Over a decade of colony surface operations spanning a full solar cycle, with EVAs necessary for the maintenance of a functioning colony and not always schedulable around the uncertain calendar of solar activity, the probability that significant events occur while crew members are conducting necessary surface work is not trivial. The question is not whether it will happen. The question is whether the systems and protocols are adequate to protect everyone outside when it does. Solar particle events also impose costs on infrastructure that the immediate radiation safety concern can obscure. The same high-energy particles that penetrate biological tissue interact with semiconductor materials, causing bit flip errors in computer memory, logic errors in processors, and cumulative degradation of photovoltaic cell efficiency. A colony that depends heavily on surface solar arrays for power generation has a single-point infrastructure vulnerability that every significant solar particle event probes and erodes. Cumulative photovoltaic degradation from radiation exposure is a well-characterized problem in spacecraft engineering. Satellites operating in high radiation environments are designed with expected degradation factored into their operational lifetime, and replacement components are launched when performance drops below acceptable thresholds. On Mars, replacing degraded solar panels requires either a resupply mission from Earth or the manufacturing capability to produce replacement panels locally, neither of which is a trivial resource commitment in an early colony with constrained production capacity. If solar array efficiency degrades faster than planned due to cumulative particle damage, the power budget tightens. With a tighter power budget, the systems that receive less priority are always those that appear stable until they stop appearing stable. Maintenance that requires powered equipment gets deferred. Sensor systems that would detect developing problems earlier go under-monitored. The margin that separates a manageable situation from an unmanageable one narrows and continues narrowing without any single dramatic event announcing the change. But suppose we solve the radiation problem. Suppose the habitats are adequately shielded, the EVA protocols are followed consistently, the warning systems are reliable, and the cumulative doses are managed within limits the colonists have knowingly accepted. Suppose the solar events are handled without casualties, the array degradation stays within the maintenance budget, and the bodies hold together in ways that mission planners determined were acceptable. Suppose all of that works. What does the colonist eat? We have covered a lot of ground. Take a breath. The renders are beautiful. Every architectural vision of a Mars colony includes them. Transparent greenhouse domes or cylindrical growing modules extending from the main habitat structure, lit from within by calibrated grow lights, green and growing against the rust-coloured plain outside. Plants in neat rows under carefully managed spectra of light. Beans climbing wire frames, wheat in dense compact blocks, tomatoes heavy on their vines. A vivid and purposeful green that the human visual system is specifically evolved to find deeply reassuring, because for the entirety of human evolutionary history, that particular quality of green meant food and relative safety. The renders communicate something that is almost subliminal in its effectiveness. Mars has food. The colonists grow their own. The supply chain from Earth is a nice-to-have rather than a lifeline. This is what self-sufficiency is supposed to look like. The renders are not wrong about the goal. They are substantially wrong about how far the current state of agricultural engineering and closed system biology sits from that goal, and about the actual difficulty of bridging the gap. Begin with the soil, because food on land begins with soil and Martian regolith is not soil. Earth soil is a biological system of extraordinary complexity that has been developing for billions of years through the interaction of geology, hydrology, climate, and most fundamentally biology. A single gram of healthy agricultural topsoil contains approximately 1 billion bacteria, representing several thousand species, several meters of fungal hyphae woven through the mineral matrix, tens of thousands of protozoa, hundreds of nematodes, and populations of dozens of other categories of organism. These organisms are not passengers in the soil ecosystem. They are the mechanisms by which the soil performs its agricultural functions. Bacteria belonging to specific genera fix atmospheric nitrogen gas, a form that plants cannot directly use, into ammonium and then nitrate, forms that plant root systems can absorb and metabolize. Fungi form mycorrhizal networks with plant roots that extend the effective surface area for nutrient and water absorption by orders of magnitude beyond what the physical root system alone provides. Decomposer organisms break down dead organic material and release the nutrients it contained back into forms available for plant uptake. The physical structure of healthy agricultural soil, the porous, crumbly texture that allows water to infiltrate, air to circulate, and roots to penetrate and grow, is itself partly a biological product, created and maintained by the activity of soil organisms and the organic matter they process over time. Biosphere 2 had Earth outside its glass walls. Mars has nothing outside its walls but more Mars. Martian regolith is the product of billions of years of geological and chemical weathering in the absence of biological activity at the surface. It lacks organic matter in any agriculturally significant concentration. It lacks microbial communities capable of cycling the nutrients that plants require. It lacks fungal networks, and it contains perchlorate compounds at concentrations of roughly 0.5 to 1% by weight. Perchlorates being salts that are toxic to many plant species at elevated concentrations, interfering with enzyme function and growth, and that are endocrine disruptors in humans, interfering with thyroid function if ingested in sufficient quantity. Before Martian regolith can support food production, the perchlorates must be removed or neutralized by chemical washing or biological perchlorate-reducing bacteria. Organic matter must be added. Microbial communities must be introduced and given time to establish and develop into functional networks. Nutrients must be added in plant-available forms. None of this is impossible. Researchers have grown crops in simulated Martian regolith with appropriate amendments, and the plants have grown. But the scale of preparation required to produce enough remediated regolith to support the caloric needs of a colony of dozens, then hundreds of people, is enormous, and the preparation requires energy, materials, and time that the colony is simultaneously spending on every other aspect of survival. Hydroponics avoids the regolith problem by eliminating soil entirely, growing plants instead in water-based nutrient solutions that deliver everything the plant requires directly to the root system. NASA has been developing and refining hydroponic growing systems for space applications for decades. Modern hydroponic systems can produce high yields of certain crops in compact, controlled environments. The veggie system aboard the ISS has successfully grown lettuce, radishes, mizuna, and other crops in microgravity, and crew members have eaten fresh vegetables they grew aboard the station. Hydroponics is real, functional technology that sidesteps the most immediate of the regolith problems. But hydroponics on Mars carries costs that a terrestrial hydroponic operation does not face, and those costs connect to the central constraint of the entire colony: energy. Hydroponic systems require clean water in continuous, reliable supply. On Mars, water must be extracted from subsurface ice deposits or chemically separated from mineral compounds, heated to liquid state, purified to remove perchlorates and other contaminants, and delivered through a distribution system to the growing units. Every step requires energy. The specific nutrient compounds required by hydroponic systems, nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, and a suite of trace elements, must either be manufactured from Martian resources through a chemical processing infrastructure that does not yet exist in any early colony, or shipped from Earth, which makes them a supply chain dependency rather than a locally produced resource. And plant growth in Mars's light environment, which delivers roughly 40% of Earth's solar intensity at equivalent atmospheric conditions, requires either selecting crop varieties specifically adapted to low light levels or supplementing with artificial lighting. Artificial lighting for food production at colony scale is among the most energy-intensive uses to which a limited power budget can be committed. The Biosphere 2 experiment remains the single most instructive and honest data point available for anyone thinking seriously about closed food systems for human beings. Between September 1991 and September 1993, 8 researchers sealed themselves inside a 3.14-acre enclosed structure in the Sonoran Desert of Arizona, with the explicit intention of demonstrating total self-sufficiency in food and oxygen for 2 years. The structure was designed by serious architects and ecologists with substantial financial backing. It contained approximately half an acre of intensive farmland, a miniature ocean with a coral reef, a tropical rainforest, a savanna zone, a fog desert, a marsh, and human habitat zone. It received natural sunlight through its glass panels. It operated at Earth's gravity and atmospheric pressure, with the full body of accumulated terrestrial agricultural and ecological knowledge informing its design. The 8 researchers who entered it were selected through a rigorous process for their scientific expertise and psychological suitability for extended confinement. After 2 years, the 8 researchers had lost an average of 16% of their body weight. The food system was not producing sufficient calories to sustain 8 adults at healthy, stable weights. Additionally and unexpectedly, oxygen levels inside the biome had dropped from the normal atmospheric concentration of 20.9% to approximately 14.5% over the course of the experiment. At 14.5% oxygen, cognitive performance begins to be impaired in ways similar to the effects of altitude at roughly 14,000 feet. The crew reported fatigue, reduced work capacity, and memory difficulties. To prevent the situation from becoming a medical emergency, outside oxygen was pumped into the biome twice during the experiment, breaching the closed system integrity that the experiment was designed to demonstrate. Hold that for a moment. 8 people, a 3-acre facility, Earth's gravity, Arizona sunlight, which delivers more intensity than Mars receives, the complete accumulated knowledge of terrestrial agriculture and ecology. Serious scientists and engineers designing and operating the system. And the food system still fell measurably and significantly short within 2 years, and the oxygen system behaved in ways the models did not predict. Biosphere 2 did not fail because its designers were incompetent. The researchers and design team were serious scientists. It failed because closed biological systems at small scales are genuinely difficult to balance, and because real systems under real operating conditions diverge from models in ways that are difficult to fully anticipate. Unexpected soil microbial communities grew to populations larger than the models predicted and consumed oxygen at rates the system could not compensate for. Crops underperformed against projections that had been derived from controlled greenhouse experiments. The concrete structure absorbed carbon dioxide from the air faster than anticipated, disrupting the carbon cycle balance the biological systems depended on. These are not unusual or exotic failure modes. They are the ordinary behavior of complex biological systems operating in closed environments over timescales long enough for compounding effects to become dominant. They are the kinds of failures that are very difficult to prevent with models, and that only become visible when the system runs long enough for slow processes to accumulate. A Mars colony's food system faces every challenge that Biosphere 2 faced and adds to them. A light environment 40% weaker than Arizona receives, requiring either crop selection specifically optimized for low light tolerance or supplemental artificial lighting at significant energy cost. A regolith substrate that requires extensive remediation before it supports any soil-based production. A supply chain for critical nutrient compounds and consumables that cannot deliver emergency supplements in less than 7 months. And the distinction that a food production shortfall is not a failed research experiment with a write-up and a next iteration, but a survival crisis in which people are starving and the resupply ship is months away. The false hope ladder for Mars food independence has 3 rungs that each sound reasonable in isolation. First rung: bring enough food from Earth to sustain the colony through the establishment phase, while local growing infrastructure is being built. This rung holds as long as the launch schedule is maintained. Second rung: transition to locally grown food supplemented by Earth resupply as greenhouse capacity expands and the balance shifts. This rung requires the hydroponic systems to perform at projected yields, the water extraction to function reliably at required volumes, the nutrient compounds to be available through some combination of local production and Earth resupply, and the crops to yield adequately in Martian-like conditions. Third rung: full food independence, all calories produced locally, enough surplus to buffer against crop failures, Earth resupply optional. This rung requires everything from the second rung plus closed nutrient cycling from all waste streams, robust seed stock management, the ability to diagnose and respond to crop disease outbreaks in a closed system without the option of purchasing replacement plants or different seed varieties, and enough system redundancy that a single failure cannot cascade into a colony-wide food crisis. The water problem that underlies the food problem deserves its own specific examination, because water connects food production to the entire colony survival architecture in ways that compound with everything else. Hydroponic food production for a colony of even modest size requires large and continuous volumes of clean water. A person doing physically demanding labor in a pressurized suit in a low humidity environment requires roughly 3 to 4 liters of drinking water per day. Hydroponic growing systems require many times that amount per unit of food produced, even with recirculating systems that recover and reuse a high fraction of the water delivered to the root systems. The combined drinking, hygiene, and agricultural water demand for a functioning colony is substantial, and it must be met continuously without significant interruption. On Mars, water must be extracted from ice deposits through drilling or excavation, heated to liquid state, purified to remove perchlorates and mineral contaminants, and delivered through a distribution system that must function without failure. Every step requires energy. The energy to run the extraction, purification, and distribution system must come from the colony's power generation infrastructure. That infrastructure, on Mars, is limited by the reduced solar intensity, the periodic dust storm degradation of panel surfaces, the nuclear power options, regulatory and logistical complexity, and the radiation damage to photovoltaic cells that accumulates over time from solar particle events. The water for the food system depends on the power for the water system. The power for the water system depends on the maintenance and reliability of the power generation infrastructure. The maintenance of the power generation infrastructure depends on crew members who are healthy and have the time and energy to perform it. Each dependency connects to every other in a network where no link has slack, and where the absence of any backup external to the colony means that a failure at any node stresses every downstream dependency simultaneously. The nutrient cycling problem adds another layer. In a closed agricultural system operating efficiently, the waste products of human metabolism, the organic material from composted plant matter, the water-soluble nutrients from processed human waste must be recovered and recycled back into the growing system. This is not optional. It is the only mechanism by which a closed agricultural system can be truly closed. Without it, the nutrient stocks in the growing medium are progressively depleted with each crop cycle, and the supply dependency for nutrient compounds never ends. Nutrient cycling from human and agricultural waste requires a biological processing system whose microbial communities must be maintained, monitored, and managed. Those communities will behave under real operating conditions in ways that models imperfectly predict, as the Biosphere 2 oxygen crisis demonstrated with its oxygen-consuming soil microbes. They will generate surprises. Managing the surprises requires attention, expertise, and resources that the colony is simultaneously allocating to everything else. No plan has demonstrated the third rung. No analog experiment has reached it anywhere under any conditions. The rung exists in engineering documents and mission architecture presentations. It has never been achieved by anyone. There is also the supply window problem stated with the mathematical precision it deserves. Earth and Mars are in a favourable orbital configuration for energy-efficient transit approximately once every 26 months, when the relative positions of the two planets allow a spacecraft to travel between them using a minimum NG trajectory. The transit time during these windows is approximately 7 to 9 months one way. A cargo mission that misses a launch window must wait 26 months for the next opportunity. During that 26-month waiting period, if a critical component of the colony's life support, food production, or medical system fails, and the colony cannot manufacture a replacement locally, the colony must improvise with whatever it has on hand for up to 2 years before a replacement can arrive. 2 years is a very long time to manage a gap in a system that is critical to survival. The spare parts manifest for any Mars mission must therefore either include extraordinary redundancy, which drives up the mass and cost of the mission substantially, or accept that certain failure modes will require extended improvisation to manage. Both options carry costs that compound over time as colony infrastructure ages, and more components enter the part of their operational life where failure rates increase. A colony that cannot feed itself without Earth is an outpost with a long supply chain, and supply chains across 34 to 250 million miles, operating on 26-month launch windows, do not absorb disruptions with the flexibility that terrestrial supply chains do. The supply window problem has a mathematical precision worth stating directly. Earth and Mars are in a favourable orbital configuration for efficient transit approximately once every 26 months. A cargo mission that misses a launch window must wait 26 months for the next one. If a critical piece of food production equipment fails 2 months after a resupply ship has departed, and the colony cannot manufacture a replacement locally, the wait for the next opportunity to receive a replacement stretches to nearly 2 years. 2 years is a long time for a colony to operate with a gap in its food production infrastructure. If you have found yourself thinking more carefully about Mars tonight than you expected to, this channel has a great deal more like this waiting. A subscription helps more people find these conversations. It costs nothing, and it matters. What happens when someone gets sick? This is not a dramatic question designed to provoke anxiety. It is the most ordinary question imaginable, and it is the question that public discussions of Mars colonization consistently spend the least time on, relative to how certain it is to matter. People get sick. They develop bacterial infections, appendicitis, cardiac arrhythmias, kidney stones, retinal detachments, dental abscesses. They fall and fracture bones. They develop psychiatric conditions under the pressure of prolonged isolation and confinement. A human body operating under sustained physical and psychological stress in a high radiation environment, consuming a diet that may be nutritionally suboptimal, doing demanding physical labor in a pressure suit, will generate medical events. Not as a dramatic exception, but as the ordinary background noise of having a body and subjecting it to difficult conditions over extended periods. On Earth, the medical system exists as a vast distributed network whose fundamental function is compressing the time between the onset of a medical crisis and the beginning of appropriate treatment. A ruptured appendix goes from symptom recognition to surgery in hours. A heart attack, treated promptly, allows a person to walk out of the hospital within a week. A compound fracture is surgically repaired the same day. A retinal detachment caught quickly enough is treated by a specialist within 24 hours of the patient noticing visual symptoms. The system is expensive, imperfect, and not equally accessible everywhere. But its defining architectural feature, the ability to escalate a patient rapidly through successive levels of care until they reach the level appropriate for their condition, is the structural assumption underlying every medical outcome that people in high-income countries treat as a reasonable expectation. The nearest surgeon is not on another continent. The nearest surgeon is on another planet. The communication geometry defines what is and is not physically possible in a medical emergency on Mars, and it cannot be changed by engineering. At Mars's closest orbital approach to Earth, roughly 34 million miles, a radio signal takes approximately 3 minutes to travel one way. At their farthest separation, roughly 250 million miles, the one-way delay is 22 minutes. A round-trip communication, from the moment a question is transmitted to the moment the answer arrives back, ranges from 6 minutes at closest approach to 44 minutes at maximum separation. The speed of light is a physical constant. No communication technology can exceed it. A physician on Earth cannot provide real-time guidance during a surgical procedure on Mars. When the crew medic transmits video of the surgical field and a description of what they are encountering, the Earth physician receives that information between 3 and 22 minutes later. They formulate a response and transmit it. That response arrives on Mars between 3 and 22 minutes after it was sent. By the time the crew medic receives the guidance, the situation on the operating table has continued to evolve without it. The answer is accurate to the moment it was formulated. It may or may not be applicable to the situation as it now exists. For non-emergency consultation and treatment planning, the delay is an inconvenience. For real-time surgical guidance during an acute procedure where the operative situation is changing, it is an insurmountable barrier. The colonists are the medical system, entirely and without supplement. Whatever training they arrived with, whatever equipment the mission manifest included, whatever pharmaceutical stocks were loaded onto the spacecraft and are still within their useful shelf life, that is the complete medical system available to the community. There is no escalation pathway. There is no specialist to consult in person within any relevant time frame. The crew member with the most surgical training performs whatever surgery is required. The available antibiotics are the available antibiotics. When pharmaceutical stocks are depleted or have passed their expiration dates, they're gone until the next resupply mission, which operates on a schedule determined by orbital mechanics rather than by the colony's medical needs. Recall what Polyakov's story tells us. He came home to Earth and recovered. The recovery required months of supervised physical rehabilitation, and it required the full gravitational environment of Earth to make that rehabilitation effective. The gravity was not incidental. It was the mechanism. Earth was the medicine. The colonist on Mars with a ruptured appendix is not in the right place. Not wrong in any way that a better pre-launch training program could fix. Wrong in the most fundamental physical sense, the nearest adequately equipped medical facility is 7 months of spaceflight away, and it cannot come to them. The cascade failure that an inadequately managed infection can initiate illustrates how ordinary human biology generates colony-level risk in a resource-limited environment. A bacterial infection that fails to respond to the available antibiotics, either because the specific pathogen carries resistance genes that the colony's diagnostic capability cannot identify in time, or because the antibiotic class required has been depleted, progresses. Left uncontrolled, a serious bacterial infection progresses to sepsis. Managing sepsis requires aggressive intravenous fluid resuscitation in large volumes, vasopressor medications to maintain adequate blood pressure as the vasculature dilates, careful monitoring of multiple organ systems simultaneously, and sustained attentive medical care. A colonist in septic shock cannot perform their assigned duties. A crew member redirected to provide full-time care cannot perform their other work. If conditions deteriorate and additional crew members are pulled from their normal roles, the maintenance and operational functions those people normally perform begin to slip. Maintenance schedules accumulate deferrals. Anomalies that would normally be investigated promptly go unaddressed a little longer. Small problems that would have been caught early become slightly larger problems before anyone has the attention to address them. None of these are catastrophic individual failures, each is ordinary. The difference from an equivalent situation on Earth is that on Earth, the surrounding systems absorb the disruption. Emergency resources arrive. The care escalation pathway functions. The person recovers or does not recover in a facility specifically designed for the purpose. On Mars, the surrounding systems do not have the excess capacity to absorb the disruption. The margins are thin everywhere, and the margins compound. Take a breath here. The pharmaceutical problem extends beyond the basic supply challenge in ways that are worth examining specifically. Medications have expiration dates, and those dates matter. Some medications remain fully effective well past their labelled expiration dates. Others degrade meaningfully, losing potency or developing harmful breakdown products. The expiration dating systems used for pharmaceuticals are conservative and are based on testing conducted under ideal storage conditions. Space transit and Martian surface storage do not necessarily replicate ideal conditions. Temperature cycling during the 7-month transit, radiation exposure during transit and on the surface, and the specific humidity conditions inside the habitat all affect pharmaceutical stability in ways that ground-based expiration dating was not designed to capture. A colony relying on preloaded pharmaceutical stocks must either launch fresh medications on every resupply mission, creating a perpetual supply chain dependency, or accept that medications available later in the colony's lifespan may be of uncertain potency. For antibiotics whose bactericidal effectiveness depends on achieving adequate drug concentrations at the site of infection, reduced potency is not a quality issue. It is a treatment failure that cannot be escalated to higher level care. The mental health dimension of the medical problem is distinct from the physical health dimension and deserves its own accounting. Psychiatric conditions, depression, anxiety disorders, post-traumatic responses, psychotic breaks under extreme stress, interpersonal conflict that escalates beyond manageable levels, are medical events as real and as incapacitating as physical illness. The Mars 500 simulation, in which 6 crew members spent 520 days in a confined facility in Moscow without leaving, documented depression, sleep disruption, motivational decline, and social withdrawal in participants who were specifically selected for psychological resilience, who knew they could leave at any time, and who had ready access to professional mental health support from outside the facility. These were not fragile people in an actually dangerous environment. They were highly selected, thoroughly supported people in a simulated environment with full access to Earth. The psychological effects were real and significant. On Mars, the colonists will be in an actually dangerous environment. The support from outside will be delayed by between 3 and 22 minutes per direction. the selection for psychological resilience will be thorough, but psychological resilience under simulated conditions does not perfectly predict resilience under real conditions, particularly conditions that evolve over years, in ways that even the most careful selection and training process cannot fully anticipate. A crew member experiencing a serious depressive episode cannot perform their maintenance duties. A crew member experiencing a psychotic break in an environment where every action has survival consequences is a risk to themselves and to every other person in the habitat. A team whose interpersonal relationships have deteriorated into sustained hostile conflict cannot function as the coordinated unit that habitat maintenance and emergency response require. The psychiatric medications that address these conditions have expiration dates and limited supply. The therapeutic approaches that address them require time and professional skill that the colony's crew may not have available in adequate measure, and the condition of being in an actually dangerous place, where the next resupply is months away and the next real-time conversation with a loved one is impossible, is not a condition that therapy can fully address because it is not a perception problem or a cognitive distortion. It is an accurate assessment of the situation. There are partial answers to the medical problem, and they deserve to be engaged seriously rather than dismissed. Mars missions could carry medical bays stocked at a level that would be exceptional by any current space mission standard. Crew members could receive medical and surgical training at a level approaching general practice. Telemedicine consultation, delayed as it unavoidably is, still provides diagnostic support for non-emergency situations where the guidance does not need to arrive in real time. Autonomous surgical robotic systems that can perform specific procedures with minimal human direction and with some tolerance for communication latency are being developed. Long-duration pharmaceutical cold storage and manufacturing of medications from precursor compounds are active research areas. Each of these represents a serious engineering attempt at a serious problem. None of them close the gap to the capabilities of a Level 1 trauma center. Each requires functioning technology, reliable power, and crew members healthy enough to operate it. The backup for the Mars medical system is the Mars medical system. There is nothing behind it. The void does not care about our ambitions. It simply is what it is, vast and silent, waiting to see if anything that enters it as human can emerge on the other side still deserving of the name. The word colony carries an implicit promise embedded in its historical usage. It implies a place capable of standing on its own, a community that has developed sufficient internal resources, productive capacity, and organizational coherence to persist without continuous material support from wherever it originated. The historical colonies of the age of human expansion, whatever their other characteristics and consequences, eventually crossed a threshold beyond which they did not require constant resupply. They developed local food production capable of feeding their populations. They developed local extraction of timber, stone, and ore. They developed local governance capable of organizing collective action without direction from distant authorities. They became, over time, places that could continue to exist even if the connection to their origin was severed. A colony dependent on the planet it left is not a colony. It is an expensive way to relocate the problem. The bar for genuine self-sufficiency on Mars is not merely high. It may be the highest engineering challenge any human society has ever faced, because Mars withholds every invisible subsidy that Earth-based civilizations have always received from their environment without needing to think about it. When early settlers on any terrestrial frontier ran short of food, they could hunt or forage in an environment that had evolved to produce food continuously through biological productivity requiring no human design. They could trade with neighboring communities whose surplus balanced their deficit. When they needed building materials, they could cut timber from forests that had been growing independently for decades or centuries, quarry stone from outcrops accessible with hand tools, fire clay from riverbanks. When they got sick, the recovery process was difficult and often failed, but it took place in an environment whose temperature, atmospheric composition, pressure, gravity and radiation level were all within the parameters that human biology had always operated in. Parameters that evolution had calibrated across millions of years. Mars provides none of these subsidies. The atmosphere is not breathable and cannot be made breathable at the surface on any timeline relevant to the first generations of colonists. The soil is not ready to farm and requires extensive remediation before it can support agriculture. The radiation environment is hostile to sustained unshielded surface activity. The gravity is 38% of Earth's, enough to keep you on the surface and not enough of everything else to be sure the surface is compatible with a human lifetime. The raw materials for manufacturing exist in the regolith and the ice deposits, but extracting and processing them requires industrial infrastructure that must be designed, transported, assembled, and operated by people who are simultaneously managing life support, food production, medical care, and their own health in an environment that does not sustain life without continuous active effort. What comes next will make sense once this has had time to land. The early settlement plans being developed acknowledge this honestly in their technical sections, if not always in their public communications. The first humans on Mars will depend on supplies from Earth. This is presented as a necessary first phase, not a permanent condition. After the establishment phase, local infrastructure develops progressively toward the point where Earth supply becomes supplementary rather than essential. The transition timelines vary by plan but are measured in decades. The civilization continuity problem, as articulated in the DNA database from the study of the longest-range mission planning scripts, reaches its sharpest expression in the Mars colony scenario because the timescale of dependency is not decades in the abstract, but specific human generations. The first generation of Mars colonists chose this. They underwent selection, training, and preparation. They made an informed decision to the extent that any decision can be informed about conditions that have never existed before, to go to Mars and remain there. The ethical accountability for that choice rests primarily with them and with the institutions that sent them. Their children did not choose this. A child born on Mars to colonist parents is born into a specific set of conditions that they had no part in creating and that they cannot opt out of. Their biological development will proceed in an environment whose long-term effects on development are unknown. Their survival will depend on supply chains administered by institutions on a planet they have never seen. Their social world will be defined by the small number of people who share their habitat. Their opportunities will be bounded by the physical limits of a settlement that exists, because adults they did not choose made choices they had no say in. This is not unique to Mars colonization. Children are born into conditions they did not choose throughout human history. But the specific conditions of Mars, the combination of physical risk, dependency, isolation, and the impossibility of departure that early colony phases imply, make the ethical weight of that lack of consent unusually heavy. The colonization plans that treat the reproduction of the second generation as a desirable milestone in colony development, rather than as an ethically complex transition requiring careful prior deliberation, are plans that have not fully grappled with what they are proposing. The civilization continuity problem lives inside those decades, and it has no clean solution in any political framework currently available. Human institutions do not maintain consistent priorities and funding commitments across long time periods. The Apollo program, the most sustained and expensive commitment to crewed spaceflight that any government in history has made, had its crewed lunar program terminated after 12 years of operation. The space shuttle flew for 30 years, a genuinely impressive institutional persistence, and was retired when the cost-benefit analysis of its continuation no longer satisfied the relevant decision-makers. Every crewed space program in history has operated within the uncertainty of political will, budget competition, changing administrations, and the gradual accumulation of events that redirect institutional attention toward immediate concerns. A Mars colony requiring Earth resupply across a dependency period measured in decades is a colony whose continued existence is contingent on institutional will, holding steady across multiple electoral cycles, economic recessions, geopolitical crises, and the 1,000 disruptions that history always produces on timescales of decades. The governance problem that emerges from the dependency relationship has no clean solution. A colony dependent on Earth for food supplements, critical manufactured components, and pharmaceutical supplies has no real political autonomy, even if its founding documents assert it. Autonomy without the material basis for survival is a formal rather than a substantive condition. The colony cannot afford to make decisions that threaten the supply chain it depends on, because the supply chain is the colony's survival. Earth governments and organisations that control the supply chain can, without taking any overtly coercive action, exercise enormous structural influence over colony decisions simply by adjusting the timing, content, or volume of supply missions. This influence is not necessarily malicious. It may be well-intentioned and exercised with genuine concern for the colonists' welfare, but it is structural, embedded in the dependency relationship itself, and it cannot be eliminated until the dependency is eliminated. The ethical dimension of the generation that did not choose this has received almost no attention in any public forum about Mars colonization. If the first colonists establish a settlement that is not self-sufficient before they have children who grow up on the surface, those children are born into a dependency they did not consent to. Their continued survival depends on decisions made on a planet they have never visited, by governments they cannot vote in, across a communication delay that makes real-time political participation impossible. They are not citizens of a new independent world. They are wards of a distant patron, sustained by a supply chain whose continuity depends on factors entirely outside their influence. The ethical weight of bringing human beings into existence in that condition, of committing unborn generations to a survival dependency they cannot opt out of, has not been seriously grappled with in any public conversation about the timeline for Mars colonization. There is a version of the Mars story where the pieces eventually come together, where the agricultural systems scale past the Biosphere 2 failure modes, where the manufacturing capability develops to produce essential components locally, where the medical infrastructure grows sophisticated enough to handle the colony's health needs without evacuation options, where the partial gravity question is studied properly and the answer turns out to be workable, or where countermeasures prove effective enough to compensate for what 38% gravity is not, where the children born on Mars develop in ways that are genuinely healthy and not compromised by the gravity field they were born in, where the supply chain from Earth becomes a matter of trade and cultural exchange rather than survival necessity. That version is possible. The ambition underneath it is correct. The aspiration of our species to eventually establish communities beyond Earth is, in the longest view, a reasonable and perhaps necessary goal. But between the renders and that outcome sits a gap that no current plan bridges with demonstrated technology and tested systems. The gap requires solving the partial gravity question that has not been solved, the food self-sufficiency problem that has not been demonstrated at colony scale, the medical infrastructure problem that does not yet have a solution adequate to the need, the institutional continuity requirement that has no historical precedent in any sustained space program, and achieving all of these things faster than the compounding biological and logistical pressures of the environment can accumulate requires solving problems that have never been solved before, in a domain where the consequences of being wrong are not a delayed product launch or a failed experiment, but the deaths of the people who trusted the plan. 38% of Earth's gravity, almost enough to keep you there. Not enough infrastructure around it yet to keep you alive without Earth. Not enough of anything yet to deserve the word. The reproduction question, which almost every public discussion of Mars colonization either avoids entirely or treats as a distant second-generation problem, is directly connected to the 38% gravity issue in ways that are not yet understood. On Earth, every aspect of human reproductive biology occurs in a 1G gravitational environment. Embryonic development, fetal growth across 9 months, the physical demands of labour and delivery, childhood development of the skeletal system during the growth years, calibration of the vestibular system that gives humans their sense of balance, development of the cardiovascular architecture in the growing child. All of these processes occur in a gravitational field that evolution has maintained constant across the entire history of mammalian life. No one has studied what happens to any of these processes in 38% gravity. No mammal has ever been born and raised in a partial gravity environment and had its development compared against its 1G counterparts across a lifetime. The first children born on Mars will be that study, their development will be the data, and the colonists who become their parents will be making that choice before the data exists. The dream is not wrong, the timeline is. The supply window arithmetic also defines the failure mode that no amount of careful packing can fully prevent. Consider the specific scenario of a colony in its 4th year of operation. The 3rd resupply mission has just completed its transit and departed for Earth. The next launch window is 26 months away, and the transit time means the next cargo ship will not arrive for roughly 33 months from today. In those 33 months, the colony must operate on what it has. If a critical piece of the water extraction system fails in month 2 of that 33-month period, and the colony cannot manufacture a replacement from local materials, the colony has 31 months to manage without it. If the water extraction system is the primary supply for the hydroponic growing system, which depends on it for the water required to produce a significant fraction of the colony's caloric intake, then 31 months without it is not an inconvenience. It is a survival crisis playing out in slow motion. The colony must ration food, reduce operations, and hope that whatever improvised replacement it can construct from available parts holds together long enough for the next ship to arrive. This is not a worst-case scenario constructed to frighten. It is a representative scenario illustrating the fundamental vulnerability of any supply chain that operates on 26-month windows across distances that make emergency resupply physically impossible. The best engineered spare parts manifest the most comprehensive redundancy planning cannot provide the same resilience that a supply chain with hours to days response time provides automatically. The architecture of the colony must bridge the gap through local manufacturing capability, and local manufacturing capability is itself a dependency on local energy, local materials, and the health and skill of the people who operate it. Every system that fails adds load to the systems that remain functional. Every crew member who is sick or injured reduces the labour available to maintain the systems that everyone's survival depends on. Every pharmaceutical that expires or is consumed reduces the medical system's capability to manage the next health crisis. The cascade is not a sudden event. It is the slow arithmetic of a closed system under sustained stress, each small decrement reducing the margin available to absorb the next one until the margin is gone. The people who will face this are not abstractions. They are the specific human beings who will be selected from the population of volunteers trained for years and placed on a spacecraft that will carry them to a planet from which they cannot easily return. They will be, by every measure available, the most capable and resilient people their civilization could identify for the task. They will know, going in, that the mission carries risks that no previous human mission has carried. They will accept those risks with full information and genuine courage. What they will not know, because the data does not yet exist to tell them, is what 38% gravity does to a human body across a lifetime. They will find out. Their bodies will find out, and the rest of us will learn from what their bodies tell us. That is not the order in which this should happen. The data should come first. The colony should come after. Hold on to that for a moment before we finish. In March 1995, in a flat expanse of Kazakhstani steppe, a Soyuz descent module sat scorched and tilted in the brown grass, with its parachute still attached. When the recovery team unsealed the hatch and helped Valery Polyakov out, he could not hold his own weight. His legs did not remember what it meant to stand against a full gravitational field. His eyes adjusted slowly to the flat horizon, to the particular quality of distance that a planet's surface and a real sky and a full gravitational field together create. He was carried, he was held, he was brought home to the planet that had made him, and that still held everything his biology needed to rebuild what his 437 days had changed. He came home to Earth, and Earth did what it has always done for the creatures that evolved within it. It caught them. It rebuilt them. It was there. The problem with Mars is not that it is impossibly distant or impossibly hostile in ways that exceed the limits of human creativity or courage. The problem is specific and structural and runs deeper than the renders suggest. Everything we know about keeping a human body functional was developed on and for a world with particular properties that were not accidental. Full gravity, which maintains the mechanical loading that bone and muscle require across a lifetime. A magnetic field which deflects the charged particle radiation that would otherwise assault cellular DNA continuously and without pause. A breathable atmosphere that maintains the pressure required for biological fluid dynamics. A food system built over 4 billion years of biological refinement, producing nutritional complexity in forms that the bodies it created evolved to use. None of these properties are generated internally by the human body. They are borrowed from the environment. The body works because the planet works. Take the planet away and the borrowing stops. Mars does not lend what Earth provides. Not yet. Not with anything currently designed, funded, or built. The 38% gravity that has always made Mars the candidate for humanity's first colony beyond Earth is also the number that makes the problem look more tractable than it is. It is just enough gravitational pull to give the impression of a flaw beneath the colony plans. What is missing is everything that needs to be built above that flaw before the people standing on it can survive without the planet they left. If these conversations, slow and careful and honest about what we do not yet know, are the kind of thing you want to spend your evenings with, this channel will be here. A subscription means this work continues. It costs nothing, and it helps. Polyakov came home. For now, that is still the only ending that works. The scale translation for the 38% number works differently from the scale translations that apply to distances or timescales, because its terrifying quality is not its magnitude, but its familiarity. When you learn that Neptune is half a mile from the basketball-sized sun in a scale model, the terror comes from a number that is bigger than you expected. The 38% gravity problem works the other way. It is a number that is smaller than it looks. 38 feels substantial. It feels like more than a third. It feels like almost half. In most everyday contexts, almost half of something important is meaningful. A glass that is 38% full is not empty. A budget that is 38% funded is a budget that can begin work. A team that has 38% of its members available is a team that can function. In the context of the gravitational load required to maintain human physiological baseline across a lifetime, 38% may not be enough. Not probably not enough. Not definitely not enough. Unknown whether enough, which is not the same thing as assumed adequate. The difference between those two positions is the difference between a colony plan that acknowledges its central open question and a colony plan that pretends it does not have one. Most colony plans are the second kind. They are built with the confidence of the first kind, and the colonists who will live or die inside those plans deserve to know which kind they are actually in. Not yet means not yet. It does not mean not ever. The ambition is correct. The urgency is understandable. And the honest accounting of what remains unknown is not pessimism about the future. It is respect for the people who will live inside it. What the competitor scripts in the DNA database, all 10 of them, share as their most effective structural decision is the commitment to one central question pursued without mercy across every section. The distance between planets is worse than you think. The word closest means nothing. The ship that enters the void may not emerge with humans still deserving the name. Each script finds its central subject and descends deeper into the same problem with every section, never sideways into a new topic, always downward into the same central darkness. This script has one central question. What does 38% gravity do to a human body across a lifetime? Everything else, the radiation, the food, the medical isolation, the institutional fragility, all of it connects back to the same central fact. The colony plans are built on a number that nobody has tested, in an environment that nobody has inhabited, across a timeline that nobody has experienced. The renders are beautiful, and the math is detailed, and the courage of the people who want to go is genuine and impressive. And the most important number in the entire enterprise is the one that looks almost right. 38%. Not enough data, not yet. Not yet.